in a really perfect world, you're testing one variable, everything else is held constant. I'll finish this up, stop here, but this way. You create two groups that are similar, but randomly assigning subjects to each group, then randomly choose which group will get the treatment. So that means, let's say it's vitamin C and cold, and then the control group who doesn't get the treatment. And then you kind of match up the participants, so about the same age, sex, all that, you take that into account. The more things you can control for, the better designed your experiment. We'll end there. So, anybody going anywhere this weekend? Huh? It's Labor Day weekend. Anything? Huh? San Francisco. Anybody else? Paris? No, okay. Have a good time. Yeah. It's not for biology.
I'm a biochemistry major. Should I be in a different bio?
You might. Go talk to an advisor in the chemistry department. I haven't. You can also look at the course the big thing that tells you. Oh, then you want to get out of here. Yeah. Because otherwise, you want to take a class that will actually count towards your major, right? Right? Okay. This won't. This will eat up a GE. And GEs are actually really important because they can even out your schedule so you're not taking death trap classes all the time. So you want to drop this, and you want to try to get into a 106 or 107 class. Doesn't matter.
Okay,
but you're going to have to take. You're going to want to have to take both.
So I don't have to take a bio before 106?
No, these are entry-level bios for majors.
Okay, then thank you.
Sure.
So the email for the question, it tells me
Oh, I forgot to do that. Yeah. Okay.
I haven't been moving wait list because I'm trying to crash
Oh yeah.
both.
Which ones?
I don't need the lab, I just need the
Right. Forget about the lab. So this here. So you're on the waiting list, right?
number 1.
Okay, that's right. We're just going to have to wait and see if people drop out. When they do, you'll automatically move up, and you'll be, since you're number 1, you'll be enrolled in the class. Okay?
So I emailed you about the class and I wanted to ask you about one of the waivers because I'm taking.
Right. So we're going to have to wait. Yeah. Okay. That's all. I can't give you a permission number because I haven't heard anything. They might open up the number of people we can accept. If that happens, then I'll give you a permission number. I don't know if you get in the class or not.
But how many people are on the waiting list?
I think there's 6 or 7, something like that.
But they come first and
They automatically go in, yeah, if they're on the waiting list. Since you can't because you've already taken the class and you didn't pass it.
but do we have any chance?
There's always a chance, like I said, a lot of times we haven't heard anything, we will soon, about whether opening up extra students.
You don't know when you.
It'll probably be next week sometime.
Okay, then I'll just.
Yeah, so I wouldn't fret too much.
Okay.
Okay? Hi.
I just need to know because I'm an extension.
Yeah.
And I can't go on my class. I'm not registered for the bio. I was registered on the physics class, but I don't like it.
What's that?
I was registered for a physics class.
Uh-huh.
I don't like it and I would like to go to the bio.
Okay. What's your major?
Biochemistry.
Oh, you don't want to take this class.
It's just for science because I need 15 units for science.
Oh, okay. It would be better if you took something like Bio 106, which you're going to need, or Bio 107 if you can get into one of those classes.
Okay.
Okay? Otherwise, I mean, if you, first of all, are you on the waiting list or not? Yeah. The chance then of getting into this class is pretty small. You're going to have to try to crash. But I would try to crash something. You could always crash, pick another GE that you'll need that actually can't be used for anything else, just for the GE that you need. But you don't want to take this class because you won't get any credit for it, really. Okay?
Thank you.
Hi, how's it going, man? I emailed you. My name is Michael, by the way.
Uh-huh.
Yeah, I was on the. I was on waitlist. I'm on number 4, but like, so like, I just want to know like, so I'm trying to get my GE social science. So would this just, yeah, would this count, right?
Yeah, so what's your what's your major?
CTBA.
What?
CTBA.
What's that?
Like cinema, television. Arts.
Oh, that, yeah,
I'm
yeah,
just
yeah.
trying to, like,
No,
get
yeah,
this,
this is a good, this would be a GE for you.
Yeah,
You need one science GE.
Yeah, like, so like I'm trying to like.
Yeah.
So I know I heard you were talking to them, so I know I pretty much just wait for like the end of the week and then see how
Well,
that
probably
goes.
probably next week will go much better.
Yeah, I mean there's a lot of open spots and maybe
Yeah, I know.
so maybe if all goes well, I feel like
Yeah.
should
Yeah. I mean, don't like freak out yet.
Oh no.
Okay?
I still want to like
Yeah.
be in this class. So like even if I like even if they won't let me like I should definitely try to go next semester. Or something.
Okay,
But
okay.
I definitely want to for sure try to get it done.
Okay, good. Okay, well, let's see. What's your name again? Michael?
Yeah. But you
Okay.
can call me Andre. That's my intro name.
Okay.
Yeah.
You can call me Mo.
Mo. Okay.
Or as long as you don't call me asshole, it's fine.
Dude,
Okay. Yeah, so,
Yeah.
okay, great.
I'll keep all. But this is the last class, so not until next week. So if
Yeah.
anything, I'll email you and check.
Yeah, I'll be out of town until next Monday.
Okay, so
So, yeah.
if I don't get a response, then.
But don't worry, I still have email and all that, so you can still email me.
Alright, thanks so much.
Okay? Good luck, Michael.
Thanks.
Oh yeah, one more thing. Okay, so can I just email you, just like to know how many kids you're able to take in? That way I will be able to know, and I will just like
Yeah, email me.
email you. Okay.
And I'll put your name on my list,
Okay.
and then we'll keep up and see what
Okay.
happens.
Okay, so then.
What's your name?
Stephanie Reyes.
Okay.
Yeah.
Oh, yeah, I know.
Yeah,
Okay, you're on the list then.
Yeah. Okay. So I just email you like around next week. Will
Yeah.
that be fine? Like
Yeah.
on Monday.
Yeah, Monday or Tuesday,
Okay,
something
and then
like
just
that.
see what happens.
Yeah.
Okay, then thank you so much.
Okay, thanks. So this is where we left off last. Now we talked about the fact that science is kind of weird in that you don't go out and try to prove that something is true, as much as you try to go out and disprove something is not true. Okay? Now, we've gotten to the point of doing experiments. Now, there's different ways of collecting or doing science. Sometimes you can't do experiments, but in this case, we're going to assume that we can. And you usually are testing the effect of one variable, let's say. In this case, we'll say taking vitamin C protects you from colds. Okay? And so, obviously, the variable, well, there's two different variables here. One is the treatment variable, and that's the independent variable, and that's whether someone gets vitamin C or not. And then there's a response variable. Do they get a cold or don't they get a cold? Okay? Now, when you set up a controlled experiment, in this case we're going to have two groups. We're going to take a group of people, we're going to split them randomly into two groups. It's not like I go, oh, all the women are going to be in the group that gets vitamin C, and all the men are going to be in the other. That's not a representative sample, is it? You want a representative sample of the actual population of individuals who are going to be taking vitamin C and whether they get any sort of benefit or not. Okay. So, you want to, and you can control for various things that you really aren't all that interested in. The main effect that we're interested in is whether vitamin C protects you from getting a cold or not. But there might be sex differences, there might be age differences. Oh yeah, by the way, part of the treatment everybody gets is a spray of rhinovirus, which is the virus that causes a cold. So you get exposed to it. People who supposedly eat vitamin C will get fewer colds. out of the total number. Okay, so you want to control for these extraneous variables. It's useful when we do statistics, which we'll deal with a little bit later. Okay. Okay, now, in this case, the variable that's manipulated, in other words, getting vitamin C or not, that's called the manipulated variable or the independent variable, or even the explanatory variable. So, we have a hypothesis, right, which is that, here's a hypothesis. Remember, hypothesis is an explanation, makes predictions. The prediction is that vitamin C will protect you from getting colds. You go through the whole, everybody gets a snort of rhinovirus. Everybody also gets a vitamin C tablet or what's called a placebo tablet. So the group that doesn't get vitamin C, it's not like you just give them nothing, because there's actually something called the placebo effect, which means that you think you're getting something, and that effect is actually measurable, and you suddenly you don't get a cold, because you think in your head that you shouldn't get a cold when you think you're actually getting the vitamin C. Okay, and then the response variable, which is called a dependent variable. Let's see. So, come on, do me a favor here. Okay, that's good enough. And then okay. Now, so here we are. Now, we're going to ask you a question here. You do a survey. That means you ask people. And you ask who takes vitamin C and how often do they catch colds, and see if is there a relationship between vitamin C and cold resistance. Or do a survey and ask who takes vitamin C, then put the vitamin takers into one group and the rest into another, and then expose each group to a mild virus and see who catches the cold, and record the differences between the two groups. Or you take a large group of subjects, you randomly divide them into two groups. That means it's a representative sample of the overall population. Similar number of men and women and ages and all that kind of stuff. And you have one group that takes a pill of vitamin C, let's say 1,000 milligrams, for 2 weeks, and the second group takes identical tablets with no vitamin C. That's the control group, or the placebo group, for 2 weeks. That way, neither group knows that they actually got vitamin C or not. They're all taking a pill, but they don't know whether they actually got vitamin C or not. And then expose them to the mild virus to see who gets the cold. Which one would you
C.
prefer? C, right? Okay. The other ones, did someone say B or A? Okay, I'm going deaf. Now, this kind of experiment is not, you can't always do these sorts of things. Sometimes, let's see, what is it? I'm trying to think. Well, sometimes the control group or the group who gets something or doesn't get something, sometimes they know whether they got something or not. Okay? So let's say you had two groups and you wanted to study the effects of cold, that means cold weather, on the different groups in terms of, let's say, getting a cold with rhinovirus. Well, obviously, in that case, you might have one group, you make them sleep out in the cold, on top of Mount Everest, and the other group, you keep them in a nice warm room. Now they know whether they were in a nice warm room or whether they were freezing their ass off on top of Mount Everest. Okay? It's like they know which group they're in. So you really can't control for the placebo effect, so to speak. Okay. But in general, this is the kind of experiment that we do, where we have one variable, and then there's some other things that you know about. So, you know about a control group. In other words, the group that doesn't get the treatment, but they think they get the treatment. But there's also problems with bias. First of all, subject bias. I just explained that in terms of if the individuals know they got the treatment or didn't know the treatment. So if they don't know whether they got the treatment or not, like with the vitamin C pills, that means that it's been controlled for, and that's called a blind experiment. The subjects do not know whether they've actually gotten vitamin C or not. Sometimes you can't do that, right? So you have subject bias, whereby you have one group that definitely knows they got the treatment. They're freezing their asses off on top of Mount Everest. And then you have the other group that is in a nice warm room. They might have a bad dream about freezing their asses off on top of Mount Everest, but they're actually not getting that treatment. Okay. So subject to volunteer bias, whoever the subjects are in the study. And it can be people, it can be plants, it can be bacteria, any sorts of things that you want, questions that you're asking. Okay? Now, we talked about this a little earlier. What is it when you have someone who wants to prove something, and what's the danger of that? Anybody remember? It starts with a C. When you're trying to prove something, and you think you know it's true. You just absolutely in your heart know it's true. Confirmation bias. Right? Okay. So, when you actually set up this experiment, or technician bias, let's say you have a bunch of technicians and we're looking at a behavioral study, and they, well, first we'll do with experiments. The person who's running the experiment cannot know who gets the treatment and who doesn't prior to the experiment. That means they don't know who's in, whether it's in the treatment group who gets the vitamin C pill, or the controlled or placebo group who doesn't. Okay? Just to make sure that, you know, you don't want to go proving something that you're almost sure is true. Right? So they're as blind as anybody else. You say, well, how do they not know? Well, everybody gets a number It's all kind of hidden in the experimental protocol. It's only afterwards, like, will you please open up the envelope to see who gets the Academy Award? They don't know beforehand, okay? And then the data speaks for itself. Okay, and then technician bias. Let's say you're doing a behavioral study and you teach your different technicians what a definition of a certain kind of behavior is. So the behavior is blinking. Okay, now how many, and the protocol is how many times does an individual blink within a defined period, let's say a minute. Okay, some technicians are, let's say, better than others in, first of all, recognizing what a blink is and how many times they actually blink. They count. Some are more accurate or precise in actually counting that. Well, if you have a technician bias, it's no big deal, even if you know that you have a technician that's a little screwy. If you add an extra variable in your statistics, when you can actually test these things statistically, so you control for that kind of bias. Okay? So, but in the best of all possible worlds, neither experimenter nor technician, they do everything right, right off the bat, and you don't have those kinds of biases. But you, in a really good experiment, you want to make sure you control for that. Oh, so first of all, do you tell the subjects which group they're in? No. It's called, they're blind to it. How do you treat the control group? Identically. So let's say instead of giving them a pill, we give each of them an injection. So it's not like, oh, well, an injection hurt, so let's not give the control group an injection since they're not really getting vitamin C. Well, you want to treat each group equally to control for the placebo effect. And then there's other things that you want to do. You want to do it at, let's say, give them the pill in the morning, between 9 and 10 in the morning, every day, same day. Okay? Sometimes you might want to randomize when they get the pill, let's say. All that is kind of spelled out in the protocol. This is the experimenter bias that I'm telling you about, a double blind. Now, when the subjects don't know whether they got the treatment or not, and the experimenter who's running the study doesn't know, it means it's a double-blind experiment. This is the gold standard, especially in medical research, things like that. Okay? Called a double-blind experiment. That way you're controlling for subject bias, experimenter bias, confirmation bias, all that kind of stuff. So, after you've done all that, you've collected the data. You might have a thing. Okay, does it seem like they have a cold, or do they actually have a cold? You can actually test for that. And that is, you can collect a swab and see if they've got a raging rhinovirus infection, because they should have lots of viral particles in their nose or in their respiratory tract. Okay? So, then, remember, we're not taking one individual who gets the treatment and one individual who doesn't. We're getting a snapshot of the whole population. In other words, we're getting an estimate out of a small sample of each group. People who get vitamin C and people who don't. Having one individual in each group won't tell you anything. Plus, you can't do any stats on it, as it turns out. So that's meaningless. In fact, the larger the sample size, the better, generally speaking, up to a certain point. So some of you may be following the election, and they give you, some candidate is behind plus or minus 3%. Well, what we're really concerned about is the margin of error. Okay, so when you read something that says 30% of people believe this and 70% of people believe this, doesn't tell you anything. Okay, there's always going to be a margin of error that is actually telling you exactly what you can measure or what you can't in terms of what's true. Okay, so we do statistics. We have a bunch of different tests that we can use, and we have criteria for judging whether something is what's called statistically different. In other words, was there any difference between a group that got, in terms of colds, between the group who got vitamin C and who didn't, right? If you had one individual in each group, you wouldn't be able to tell anything. Let's say you had 3 individuals in each group. That very small sample size. And one group had one woman and the other group had 2 women. And then vice versa in terms of the men. Okay. And then you had another group where there's, let's say, 30 individuals in each group. Now, just so you know, if you know what the population is, I think the population of California condors now is like 116 out in the wild. You don't need any statistics to determine, let's say, how many are males and how many are females. You go out and count them. But in a lot of cases, you want to take a sample because the population is much too large to count every individual. Okay. So, no, I don't have a okay, let's say percent heads. The first group, there were 6 heads when you flipped the coin 10 times. And then there was 5 heads the next time you flipped it. And then you flip it a third time, and there's another 5. And then finally there's another 5, and you add all those up, and you end up with group 1 had 21 heads. And the second group, the first time you flipped the coin 10 times, only 2 heads came up. Then 7, then 5, and 5, and then that's 19. So now you would expect with a coin with heads or tails, 50% chance of getting either. Okay? In this case, though, because you're only flipping the coin 10 times, there's a chance that you'll end up getting 7 heads, or 6 heads, or no heads. You could actually flip a coin 10 times, and just because of that sample, you end up with 10 tails. Okay? Now, the greater the sample, the more likely you are to converge to the mean, and the mean is 50%. So let's say each of these groups, you flip the coin 100 times. Instead of 6 out of 10, you ended up with 61 out of 100. The next group, it was 50 out of 100, 54 out of 100, 57 out of 100, and 55 out of 100. The next group, it wasn't 2 out of 10, it was 25 out of 100. Okay? Now, let's say it was 1,000. When you do it 10 times, you have a chance of missing what would be expected, which is 50%, by 10 percentage points. So the difference between 60%, 6 out of 10, and 5 out of 10 is 10 percentage points, right? Out of 100, it's 1 percentage point, right? Out of 1,000, it's 1,000th of a percentage point. So if you did it, flip the coin 1,000 times, and you end up in one case with 522 heads and the corresponding number of tails. Okay, so the bigger the sample, the better. Okay. So, because you're having a sample and you're not measuring the whole population, you want a representative sample. That means you want a sample that is representative of the overall population. When you don't get that, you have problems. And I'll give you a very good example. There's this therapy for women who undergo menopause. It's estrogen replacement therapy, so they don't get hot flashes. Now, initially, this is one of those things about assumptions. Initially, it was thought that women who got estrogen replacement therapy, they didn't suffer bone loss the same amount, that they were protected to a certain extent from cancer versus the group that didn't get it, and they didn't have as much heart disease. Okay? Now, these were assumptions. These were not tested. And then what they did was, and they did this from an observational study, where they went back and they took a group of people who got therapy and a group of people who didn't, of women who didn't. And that's what it showed. Well, then someone finally decided that, well, maybe we should actually test this and do what's called a double-blind study. So what they did was they enrolled a whole bunch of women into this study. Individuals who got the therapy were one group. Individuals who didn't get the therapy were the other. They had, 5,000 women in each group, something like that. It turns out what they thought, using this observational study data from previously, what they thought was wrong. It turns out that there was a little bit less bone density loss with women who got the therapy, but they had a much higher incidence of breast cancer that was actually sensitive to estrogen. And they also had more heart problems, like heart attacks, things like that. How could they end up with such different results? Well, it turns out it was very simple. Most of the women who they had surveyed before were going to a doctor. They were getting the therapy from the doctor. They were, in general, a pretty healthy population, right? They were getting checkups and all that kind of stuff. The other group that wasn't getting it, they weren't going to the doctor. They were, in fact, a less healthy group. They were lower in socioeconomic status. They didn't have the money to go to the doctor. All the things that go lower were socioeconomic. Their diet wasn't as good, all that kind of stuff. So in that case, they were comparing two different samples that were not representative of the whole population. So now, with a large sample size, as I was mentioning, let's say versus 3 versus 30 individuals in the study, a large sample size, you have much better control. You have more likely to have a representative sample, and you can actually handle the variation that you see, like I showed you with flipping the coin. If you have 10 flips, there's a chance plus or minus 10% difference. You have, let's say, 100 individuals, plus or minus 1% difference. So you are much more precise in your numbers. Okay. So here's vitamin C. The percent subjects with colds and not colds, and then what the dosage of vitamin C was. Okay? Now, if this was a group where you had a total of Okay. 3 individuals for each, right? So there's 3 people here and 3 people here. You might end up with error bars. And error bars here that they overlap, and you wouldn't actually be able to tell whether there was a difference or not, even though only one, let's see, 5 people got colds with 1,000 milligrams, and 90% or 10%, 10% got colds with vitamin C, and 90% without. Okay. So in this case, even though there seems to be a really huge difference here, just because of the sample size alone, you wouldn't actually be able to detect the difference. Now, let's say, let's see, what do I want to do here? Okay. Okay, same thing here. No, cancel. Okay. Next, here we have error bars with 100 individuals. And they don't overlap. So you can have something that looks like it's really statistically significantly different, like we showed in the previous slide, that's not significant, and something like this that doesn't look like there's very much difference, 60% to 50%, and it is statistically significant because you have a sample size of, let's say, 100. Everybody understand that? Big sample size, good. Small sample size, bad. Okay. Now, a well-controlled experiment is not always possible. As I mentioned, putting one group up on top of Everest and the other in a warm room to see how that is. This is kind of the experiments that the Nazis did on Jews to see how cold affects human beings. So, and there's a lot of things where you cannot ethically do certain things to certain people that it just doesn't, fly right. Okay, so you can't always control experimenter bias and subject bias and that sort of things. Sometimes you can't get a big enough sample size. In a laboratory setting, it's easy to control for all the extraneous variables so that you're really only testing one variable. But what happens if you go out into the field? As an ecologist, I'm interested in animals that disperse seeds. And some of the animals eat some of the seeds, and they also plant some of the seeds to come back and get them later. Okay? Now, you can do this in the lab. The thing is, animals don't always, let's say chipmunks, don't always act naturally in the lab. Sometimes they're freaked out, and all they do is they sit in their nest box and never come out. So instead, I built these large enclosures, 10 by 10 meter enclosures, released animals into it with a certain number of seeds, and then they went around and these seeds were labeled with a radioactive isotope. So I could actually go with a Geiger counter and find out where they were, how deep they were buried, all that kind of stuff. Now, when I release the animals in, I might release them all in the morning, but weather changes, season changes, all these kinds of extraneous variables are happening that might actually affect the results. So I don't have complete control over all my variables. However, the animals at least are acting normally in this large enclosure compared to in this thing that's maybe 10 feet by 10 feet with sand on it, and they can cache it that way. So then there's also situations where, like we did with the survey, about individuals, women who are actually taking estrogen versus those that weren't. We're just finding out, okay, these women are in this group because they took estrogen, the other ones they didn't, right? Sometimes that's all that's possible. So in that case, you can still do a statistical analysis on that, but because you're not really controlling about who gets treatment and who doesn't, you have weaknesses in the study that you're actually doing, but sometimes that's all that's possible. Or you have what are known as sciences, historical sciences, like geology. When you go and look at a geological record, and you look at layers, let's say sedimentary layers, when they were laid down, that's what it is. It's not like you can go back and apply which fossils go on which layer and all that kind of stuff. It's just what you see is what you get. It doesn't mean the data aren't any good. It just means that you can't do a standard controlled experiment on those. And you usually get somewhat weaker inferences, but not necessarily. It's kind of like you come home, you enter your bedroom, all the glass is broken in the windows. You wonder what the hell happened. Turns out there's a baseball in the room now. That wasn't there before. And across the street is a baseball diamond. Now, you can make a pretty strong inference that it was because someone threw or hit a ball and it entered your window and broke the glass. Now, of course, maybe the glass was just broken and the baseball was in your room, but you never found it. And there wasn't a baseball diamond right across the street, but 2 streets over, and some monster comes up and hits a huge home run, and that's never happened before. So in those situations, sometimes you can make a very strong inference, sometimes you can't. As we'll get to when we do evolution, the last major great extinction, the ones that knocked out all the dinosaurs except for the birds, it looks like the smoking gun was an asteroid impact that was 110 miles in diameter off the coast of Yucatan. And it killed, I don't know, 70% of all species on the planet, including the dinosaurs. Now, if we hadn't found that, there were a whole bunch of different hypotheses about what caused that mass extinction. There was also, back in those days, there was a lot of volcanic activity. There's changes in climate that vary over these long cycles, Milankovitch cycles, like the last ice age, which was a mass extinction, not at the same level, but it ended about 12,000 years ago. We know that wasn't caused by an asteroid impact. We know that it was most likely the kind of natural variation, because it turns out the Earth's orbit is not entirely, it's elliptical, not entirely circular, and it varies over time. So some of that historical stuff, you can actually get pretty good inferences if you identify certain things that coincide very closely. But I just want you to know, you can't always do what's called a nice, perfect little experiment. Okay. So you can read these. We'll keep going. So here we are with the scientific method again. Remember, you start with observations or theory, because you've been thinking a lot. And then you go through this whole cycle. Here we are with theory again. A theory is not an opinion. When someone says, oh, it's only a theory, like gravity is only a theory, is different than a scientific theory. It's a different animal entirely. So, let's say the theory of gravity, first proposed by Newton, then Einstein's theory of general relativity. It's a larger construction. It makes, sometimes a theory has many different kinds of sub-hypotheses to it. And it makes very specific predictions. It's not an opinion. So there's a great deal of discussion for some reason in this country about whether evolution by natural selection is true. Some people think, well, intelligent design. There's a creator that created everything. And the Earth is, let's say, only 6,000 years old, right? On the one side, now you can actually test that by showing, in fact, the world isn't. You can disprove it pretty easily. You can actually date rocks with radioactive isotopes, and you can find out how old they actually are. And you can make some predictions about if there's an intelligent designer, why do we have things about, let's say, us, that don't seem very well engineered. Like the fact that even though I love to eat a nice big ribeye steak, if I'm not careful and I'm really hungry, I might have a nice chunk go down the wrong direction, and I might choke to death. Now, it's a very easy fix if a designer, let's say an engineer, engineered a human being. You'd have two different pathways that never cross. So happens you do have pathways that cross. It's a holdover, evolutionary holdover. But anyway, so a theory, like the germ theory of disease, that means microbes, whether they're virus, bacteria, fungi, all sorts of different things, are actually what causes disease versus someone put a curse on you. And that person got sick and they died. You know, witchcraft. Okay? So, theories are larger, they describe a larger phenomenon. They often have various sub-hypotheses. They make very specific predictions. If you test a theory and one of the major predictions is refuted, well, the theory usually falls. That means if it's wrong, it's wrong. Okay. Anybody in here trust this guy? Huh? You all trust him? Look at those eyes. Does that look like trustworthy eyes? Anybody? God. I guess some of you really do trust him. Okay. My love for you is not just a conjecture or an opinion, it's actually a theory. And you can trust this guy. I just want you to know that. Just look in his eyes. Trustworthy, I swear. Okay. Let's see. What do I want to do? Let's open up Top Hat.